Intraocular lenses are probably one of the most confusing topics in ophthalmology, not because they are difficult, but because there are too many options, too many materials, too many designs, and very little clarity on why one lens behaves differently from another. Most of us learn IOLs as names PMMA, hydrophobic, multifocal, toric, but we are rarely taught the optical logic behind them. In this series, we will slow this down. Most of us learn the IOLs in fragments, a little material science here, a few lens names there, and a long list of pros and cons that are hard to connect. This series is designed to build that connection. We will start from the foundations, what an intraocular lens actually is, where it sits inside the eye, and why its material and geometry matters. Then we will move step by step into the optics, how lenses bend light, how aberrations arise, and how design choices influence the real world vision. From there, we will discuss the modern IOL designs like monofocal, multifocal, toric, extended depth of focus lenses, not as brand names but as optical concepts. Finally, we will connect all of this to the clinical decision making, how to choose the right lenses for the right patient, and why the same IOL can perform very differently in different eyes. This is module 1 of our series on intraocular lenses. The approach here is deliberate. We will start with the basics, ensuring clarity at an undergraduate level, and then progressively build towards advanced clinician level understanding in the later modules. What exactly is an intraocular lens? An intraocular lens, or an IOL, is an artificial optical implant that replaces the natural crystalline lens of the eye after the cataract surgery. Its primary role is simple: to restore the refractive power that is lost when the natural lens is removed. The human eye has two main refractive elements: the cornea, which contributes about 43 diopters, and the crystalline lens, which contributes roughly about 15 to 20 diopters, depending upon the age and accommodation. Together, they form a finely balanced optical system. When we remove the crystalline lens during the cataract surgery, we are removing a significant portion of the eye's refractive power. If we do not replace it, the patient is left aphakic, severely hyperopic, functionally disabled, and dependent on thick spectacles. That is why an IOL is not optional, it is optically mandatory. Before intraocular lenses, the cataract surgery meant aphakia. Patients wore plus 10 to plus 12 diopter spectacles, heavy, distorting, and functionally disabling. The turning point came during World War II. Sir Harold Ridley, an ophthalmologist in the Royal Air Force, noticed something remarkable. Pilots with fragments of PMMA cockpit canopy embedded in their eyes showed very little inflammatory reaction even after years. This observation led to a radical idea. If this material can stay inside the eye without reaction, why not replace the crystalline lens with it? In 1949, Ridley performed the first successful intraocular lens implantation using the PMMA lens. In modern cataract surgery, the ideal position for an IOL is inside the capsular bag in the posterior chamber. This location provides the best optical alignment, long-term stability, and biocompatibility. However, there are situations where the capsular bag may be compromised due to trauma, zonular weakness, or an intraoperative complication. In such cases, lenses may be placed in the ciliary sulcus or fixated to the iris, or in selected cases placed in the anterior chamber as well. For now, it's important only to know that the IOLs can sit in different anatomical locations and not just in the capsular bag. We'll analyze their optics and complication later in the series. Now that we understand what an intraocular lens is and where it sits inside the eye, we come to a critical question. What should this lens be made up of? Because unlike an external optical device, an IOL must remain inside the eye for decades, optically clear, mechanically stable, and biologically inert. To understand this, we'll first look at what materials exist, and then we'll slow down and understand why their properties matter. Over the decades, several materials have been used to manufacture intraocular lenses. The major ones you'll encounter are the PMMA, silicons, acrylics, both hydrophobic and hydrophilic acrylics, and Collamer, which is primarily used in the phakic IOL. To understand the IOL materials properly, we first need to understand the properties that matter and then revisit each material through those properties. Let's discuss them one by one. The first one is the transmittance. Transmittance refers to the amount of incident light that is allowed to pass through a material. An ideal IOL should transmit nearly all visible light with minimal scattering. The PMMA lenses naturally have a very high transmittance, which means they allow almost all the visible light to pass through them, which is why their optical clarity is still considered excellent. However, the natural aging crystalline lens, it tends to absorb the ultraviolet and short blue wavelengths, often offering the retinal protection from the UV light. When we remove the natural lens, we lose this protective filter as well. That is why the modern IOLs include UV filters and often blue light filtering chromophores. This provides retinal protection but with a trade-off. Slight reduction in the scotopic dim light vision and subtle changes in the contrast perception is seen. So clinically, higher transmittance improves clarity, but selective filtering using the chromophores improves retinal safety. Across multiple studies, PMMA consistently demonstrates the highest optical transmittance and the least light scattering. Among the foldable lenses, clear hydrophobic acrylic transmits slightly more light than the silicone and hydrophilic acrylics. Hydrophilic acrylics tend to show slightly lower effective transmittance due to the hydration-related scattering. Yellow or blue light filtering IOLs selectively reduce transmission of the short wavelength blue light, typically below the 500 nanometer. The next property is the refractive index. Refractive index measures how strongly a material bends light. The average refractive index of the eye is approximately 1.40. And IOL materials range from about 1.40 to 1.56. A higher refractive index basically means that the bending of light is going to occur at a greater degree. It also allows the same optical power within a thinner lens. Clinically, this means thinner optics, easier folding of that optic, smaller incision to insert that IOL, and better wound stability because of the smaller incisions. However, higher refractive index also increases some problems: reflections, external reflections, edge glare, and dysphotopsias. The external reflections that you see because of the higher refractive index is also known as the cat's eye effect. So again, it's a trade-off. As you can see from the table, the hydrophobic acrylics have the highest refractive index among the commonly used IOL materials. Then they are followed by the PMMA, Collamer, silicone, and the lowest refractive index exists for the hydrophilic acrylic. The question is, why does hydrophobic acrylics have the higher refractive index than the hydrophilic? Hydrophobic materials contain less water and have denser polymer packing, leading to the higher refractive indexes. Water lowers the refractive index, and therefore hydrophilic lenses which have a greater amount of water in them naturally have lower refractive index compared to the hydrophobic acrylic lenses. The next property is the Abbe's number. The Abbe's number basically is a mathematical calculation which calculates how differently a material bends different wavelengths of light. It is calculated using the refractive indices measured for the blue light, yellow light, and the red light. The normal optical system of a human eye has an effective Abbe number of approximately 47. Most IOL materials fall within a range of 30 to 60%. So there is an inverse relationship between the Abbe number and the chromatic dispersion. A higher Abbe number means lower chromatic dispersion, so all the wavelengths of the light are going to focus more uniformly on the retina, producing a sharper image. A lower Abbe number means greater dispersion of these colors, leading to color fringing and reduced contrast sensitivity. Let us now understand the relationship between the refractive index and the Abbe's number, which is a very important concept in IOL optics. There is an inverse relationship between the refractive index and the Abbe's number. To increase the refractive index of an intraocular lens material, Manufacturers often modify the polymer structure by adding aromatic rings, sulfur containing groups, or halogenated compounds. These additions increase the material's ability to interact with light. Because of the stronger interaction with the light, light will slow down more as it passes through these materials, and when light slows down more, it bends more. This is what we mean by the higher refractive index. In simple terms, an optically dense material holds on to light for a longer time and bends it more strongly. However, this strong interaction does not affect all the colors of light equally. The blue light, which has a shorter wavelength, is affected more than the red light, which has a longer wavelength. As a result, the blue light will bend more than the red light. When different colors of light are bending by different amounts, chromatic aberration occurs. So, as the refractive index increases, the chromatic aberration is also increasing, resulting in the lower Abbe's number. And this is why they have an inverse relationship. Now, the PMMA behaves differently. Polymethyl methacrylate has a simple and a uniform polymer structure. It does not rely on the heavy chemical additives like the aromatic rings or halogens to increase its refractive index. Because of this, PMMA has a uniform electron distribution and is considered optically very pure. Its refractive index comes from its basic molecular structure rather than from these highly polarizable groups. As a result, PMMA can still bend light reasonably well while keeping different wavelengths of light bending in a similar way. So PMMA has a moderately high refractive index combined with very high Abbe's number, which explains why it is optically one of the cleanest IOL materials. The only problem with PMMA is that you cannot fold it. Modern foldable IOL materials accept the trade-off between the higher refractive index and the lower Abbe's number, and to manage the increased chromatic aberration, they rely on advanced optical design, which we will discuss in module number 2. The next important property of material is hygroscopy. Hygroscopy refers to how much water a material absorbs. Now, before we move further, let's clarify one very small but important term: hydrophilic and hydrophobic. Hygroscopy tells us how much water is inside the lens material, but hydrophilic or hydrophobic tells us how water behaves on the surface of the lens. If water spreads out on the surface, we call it hydrophilic. This means a low contact angle. If water beads up, we call it hydrophobic. This means a high contact angle. This surface behavior explains why cells and proteins interact differently with different IOLs. Approximately, the hydrophobic acrylic has less than 1% of water, and hydrophilic acrylic has 18 to 38% of water. Here, I would like you to stay focused on these two lenses because there's a clinical aspect attached to it. Higher water content makes a lens softer, more flexible, and easier to fold. Therefore, hydrophilic acrylic lenses are softer compared to the hydrophobic lenses, they are more flexible, and they are easier to fold compared to the hydrophobic acrylic lenses. But there's also a problem. Because of excessive water content, they allow greater lens epithelial cell migration, and these lens epithelial cells which have migrated behind the IOL leads to posterior capsule opacification. So there are also higher rates of PCO formation in hydrophilic acrylic lenses. So remember that. While hydrophilic lenses have higher PCO rates, hydrophobic lenses have their own problems. They can form glistenings. What are these glistenings? Glistenings are fluid-filled microbubbles or microvacuoles that form within the optic of the hydrophobic acrylic lenses. They occur here because of the temperature fluctuations that occur within a hydrophobic lens. Moreover, the material has very low water content. This leads to microphase separation within the material, and tiny water droplets or tiny pockets of fluid get accumulated within the lens material. These fluid pockets are going to cause scattering of the light, leading to a sparkling or shimmering reflex. These are known as glistenings. Glistenings can reduce contrast sensitivity. However, they rarely affect the Snellen visual acuity. So hydrophobic acrylics offer low PCO rates but at the cost of potential glistenings. Next, we'll talk about the surface properties. Another reason why PCO formation is less in case of the hydrophobic lenses is also because of their property of capsular adhesion. Let's understand why hydrophobic acrylic sticks better to the posterior capsule. Hydrophobic acrylic lenses, they adhere tightly to the posterior capsule because of the surface chemistry. Their surface promotes adsorption of the proteins like the fibronectin, which will create a really strong capsule lens adhesion. Now, this mechanical sealing effect prevents lens epithelial cell migration and also reduces the PCO formation. The next property that we are going to talk about is the biocompatibility. Okay, so biocompatibility here has two components. An IOL should be biocompatible with the uvea and also with the capsule. If there is uveal biocompatibility, there will be less chances of inflammation because most of the inflammatory cells are coming from where? They're coming from uvea. Then, if there is capsular biocompatibility, the chances of PCO will go down. Another property of the materials is the glass transition temperature, or the TG. It is the temperature at which a polymer transitions from a rigid glass-like state to a soft rubbery state. This property is particularly relevant when we're talking about the foldable intraocular lenses because it determines how the lens will behave during your loading, injection, and unfolding of the lens inside the eye. Silicone IOLs have an extremely low glass transition temperature, often well below the room temperature. As a result, they will remain soft and elastic all the times, unfold rapidly inside the eye, and they're very easy to inject. Hydrophobic acrylic IOLs, in contrast, have a glass transition temperature close to room temperature. Below this, the lens is relatively stiff, and above this, it becomes flexible. Now, this explains a common surgical observation. Hydrophobic acrylic lenses may unfold slowly, especially in colder operating rooms, and require controlled manipulation during implantation. Do observe this in your OTs and let me know in the comment section if you have already observed this. So far, we have discussed individual material properties like transmittance, refractive index, Abbe's number, hygroscopy, surface behavior, and also the glass transition temperature. Now, let's apply these properties to the actual IOL material. Think of this as building a ladder. Each material is simply a different combination of the same properties. The first one is the PMMA. PMMA is optically excellent. Remember this. It has higher transmittance. It has a high Abbe number. High Abbe number means it will have low chromatic dispersion and it has minimal chromatic aberration. This is why PMMA lenses still produce some of the clearest retinal images. However, the problem with PMMA is that it is rigid. It is non-foldable, it requires larger incisions leading to surgically induced astigmatic recovery, and there are problems associated with healing. So PMMA represents the optical gold standard but the surgical limitation. Next, we have the silicone lenses. Silicone lenses are highly flexible due to their very low glass transition temperatures. They will unfold rapidly and they are easier to inject, making them surgically convenient. Optically, they have good transmittance, not as good PMMA, but they have reasonably good transmittance and a reasonably higher Abbe number as well. However, the problem with silicone lenses is that they interact poorly with silicone oil and can accumulate deposits on their surface, limiting their use in certain clinical scenarios like the retinal patients or patients who have undergone those who have silicone oil in their eyes. Then we have the hydrophobic acrylic lenses. These are the most commonly used in modern IOLs. Okay, they have higher refractive index leading to thinner optics. They have low water content. That means they have low hygroscopy. Moreover, their surface chemistry promotes fibronectin absorption from the posterior capsule, leading to a strong capsular adhesion and low PCO rates. However, lower water content also predispose them to glistenings, microvacuoles formation that can cause light scatter and reduce contrast sensitivity. So hydrophobic acrylic lenses offer excellent stability and low PCO with a trade-off in potential optical scatter. Then when we talk about the hydrophilic acrylic lenses, they contain significant water content, making them soft, flexible and highly biocompatible with the uveal tissues. So uveal biocompatibility, think about hydrophilic. Capsular biocompatibility, think about hydroinflammatory eyes. However, their surface does not promote strong capsular adhesion. Moreover, because of the water content, this allows greater lens epithelial cell migration, resulting in higher PCO rates. Their higher water content also contribute to increased light scatter and glare compared to hydrophobic material. Then we have Collamer. Collamer is a collagen-based polymer designed primarily for the phakic intraocular lenses. It has higher water content, excellent biocompatibility, this makes it suitable for placement in eyes with an intact crystalline lens. For the beginners, let me tell you that Collamer or the phakic IOLs are basically a type of refractive surgery wherein we are not removing the crystalline lens, we are just supplementing the crystalline lens with another lens on top of it. And those lenses are known as phakic IOLs because they are placed in a Alright, this module laid the foundations, materials and their optical behavior. Next we'll focus on the IOL designs and the optics where small design differences create large clinical outcomes. Subscribe to continue with the series and I'll see you in the next module.